We are discussing a possible mechanism to implement a second-order transfer function with the LCR resonator. We have seen that basically the idea is to start from the parallel between the capacitance, the inductance, and the resistance, and then provide the input in many different ways in order to set the zeros value. What we have seen is that no matter what input we are actually applying, the pole positioning is unaffected because the pole positioning depends on the pure component of the circuit without taking into account the effect of the input. Yesterday, in particular, we went through the analysis of the implementation related to the low-pass filter, the high-pass filter, the band-pass filter, and finally the notch filter. So the idea is that with the notch, we have the input provided at this node where we face the parallel between the capacitance and the inductance. So we found that the zero location is the distance of the zero location with respect to the origin is given by this formula, which is coincident with the so-called omega null angular frequency. So basically, the idea is that the transfer function associated to this circuit is something like this. That is S22 plus omega n, the value of the zero angular frequency, omega n22, divided by the conventional expression of the denominator, that is S22 plus S time omega null over Q plus omega null to 2. Okay, in this specific case, omega null is equal as to omega n. Okay, and equal to the square root of 1 over LC. Okay, so in this way we can implement the notch filter related to this configuration here. Okay, this one. But we may be interested in implementing also different configurations in which omega n is different from omega null. To do so, we have to change a little bit the circuit, and in particular, we can base our analysis on this configuration. So we have an initial branch, which is again consisting in an inductance plus a capacitance. And then we have a second branch in which we have the resistance, but also an additional capacitance and an additional inductance. So we can call this inductance here L1, C1, this is R, this is C2, and this is L2. And this is the output voltage. Well, this configuration here seems to be slightly different from the others, in the sense that when we null the input, we have the parallel of L1, C1, R, C2, and L2. So this circuit here is somehow different from the RLC resonator. So the circuit on the left may have different poles with respect to the circuit on the right. Unless we make this assumption. If we assume that C1 parallel to C2 is equal to C, and that L1 parallel L2 is equal to L, then the two circuits are again the same. By the way, C1 parallel to C2, by virtue of the property of capacitances, is equal to C1 plus C2. While the parallel of L1 with L2 is given by this formula, L1 times L2 divided by L1 plus L2. So if you want the expression for inductances in parallel is similar to the one of resistances, okay, in parallel. So we must verify that the capacitance is equal to C1 plus C2, the original capacitance, and the original inductance is equal to L1 times L2 divided by L1 plus L2. Okay? So if this is the case, then the omega null value for this circuit, but also for this one, is constantly 1 over LC. Now, the problem is, okay, so if we have these conditions, the pole positions are unaffected. But what about the zero positioning? Well, still we have to apply the same machinery, which is based on assuming the voltage divider effect between an impedance Z1 and the impedance Z2. Okay, it's the same concept that we have analyzed multiple times in the yesterday. Okay, so the idea is that we need to fulfill two possible conditions. One condition is based on having Z2 equal to 0. And the second condition is the one related to Z1 equal to infinity. Well, Z2 equal to 0 must also be conditioned by the fact that Z1 must be different from 0. Okay, if you remember. Because the idea is that the transfer function here is Z2 over Z1 plus Z2. Okay, so we wanted to null this expression. So when Z2 is equal to 0, well, Z2 is equal to 0 when we have essentially a short circuit between this node and the ground. This could happen in two ways. So when omega is null, so at 0 frequency, because at 0 frequency L2 is a short circuit. So Z2 is equal to 0 when S is null or S is infinity, because at infinity the capacitance is a short circuit. But unfortunately, in both these conditions, even L1 and C1 are respectively a short circuit. Okay, so this means that condition number 1, which is Z2 equal to 0, Z1 different from 0, is never fulfilled. The good news is that Z1 equal to infinity is the same condition that we have applied for the previous case. Okay, so the only difference is that in the previous case we had C and L, and now we have C1 and L1. Okay, so this condition indeed it is valid for omega n equal to 1 over the square root of L1 C1. Okay, and we have two roots indeed. Okay, just like before. Okay, so the expression of the transfer function is the same. The only difference is that in the previous case, omega 0 was equal to omega n. In this new case, omega 0 is indeed equal to the square root of 1 over LC, while omega n is equal to the square root of 1 over L1 C1. Okay, so we have two extra degrees of freedom to set in a different way omega n with respect to omega null. So by tuning properly the parameters of the circuit, we can achieve one goal like implementing a high pass notch or implementing a low pass notch. So how indeed can we implement a low pass notch? Low pass notch is related to the case in which omega n is larger with respect to omega null. So the distance of the zeros from the origin is larger with respect to the distance between poles and the origin of the complex plane. So how can we achieve that? Well, we have to apply this formula to this inequality, So basically we have that 1 over L1 C1 must be larger than the square root of 1 over LC. These are both positive values, so we can cancel the square root and flip numerators and denominators. This means that LC must be larger than L1 times C1. Okay, from this expression, it follows that we have this result. Okay, but LC are related to L1 and C1 by this formula. Okay, so we can substitute C with C1 plus C2 and L with L1 times L2 divided by L1 plus L2. Okay, so the idea is that L1 parallel L2 must be times C1 plus C2, that is L times C, must be larger than L1 times C1. What we can do is to check the inductance part and the capacitance part separately. So we can verify that, for example, C1 plus C2 is larger than C1. And this is obviously true, okay, because we have an extra term here, so this is okay. What it is not okay is the fact that L1 parallel L2 must be larger than L1. This is impossible because anytime we have a parallel between two inductances, the resulting inductance is smaller than the smallest one. Okay, pretty much like when we have a parallel between resistances, the resulting effect is a smaller resistance with respect to the two independent components. Okay, so R1 parallel to R2 is always smaller than R1 or R2. Okay. So how can we cope with this problem? Well, we can zero L2. Okay, if we remove L2, what we get is let's say, rather than zeroing, let's say that we extract L2 from the circuit. In this case, we don't need to compute the parallel. Okay, but we have just L1. So if we transform the circuit in the following way, we achieve the desired goal. So at the same time, we can control the pole positioning the zero positioning and be sure that we are implementing a low pass notch. When we wanted to implement an high pass notch, the situation is just the opposite, in the sense that high pass notch are realized when omega n, the angular frequency of zeros, is smaller with respect to the angular frequency of poles. This means that L1 C1, which set the value of omega n, must be larger with respect to LC, which set the value of omega null. Since LC and L1 C1 are inversely proportional to omega n, we have to change also the orientation of this inequality. So this means that L1 C1 must be larger than L, which is also the parallel between L1 and L2, time the parallel of C1 and C2, which is C1 plus C2. Okay. If we analyze the independent, the two different conditions, so if we force L1 to be larger to L1, L2, and C1 to be larger than C1 plus C2, then we clearly are okay with this part, but we are not okay with this one, because C1 cannot be larger than C1 plus C2 in general. Okay, so the only way to get the desired result is exploiting the fact that L1 is always larger than L1 parallel L2. And if we null C2, we get the result that basically C1 is equal to C. Okay, so in this inequality is accepted. Okay, so basically the new version of the circuit is provided in the study material. Where you can find all the different combinations. Okay, so low pass notch, the one that we have seen before, and also high pass notch. Okay, so in this case, we have just one capacitance. So all the combinations have been realized. All the combinations but one, that is the all-pass filter. So the all-pass filter is realized in this way because basically, well, the transfer function that we have to implement is given by this expression. So S22 minus S omega over Q plus omega 22 over S22 plus S omega null over Q plus omega null 22. Okay. So if we had to this numerator a given quantity, let's say asterisk, and then we subtract asterisk, we are clearly okay. Okay, we are not doing, we are not harming the original transfer function. So suppose that the quantity asterisk is equal to S omega null over Q. So we can rewrite the transfer function in the following way. S22 minus S omega null over Q plus omega null to 2 plus S omega null over Q minus S omega null over Q. And we keep the denominator like before. So S to 2 plus S omega null over Q plus omega null to 2. Well, now if we look at this part of the numerator, this part of the numerator is equal to the denominator. Okay, so what we can do is to rewrite the transfer function as 1 minus S omega null Q, S omega null Q, so S omega null Q taken 2 times. And the conventional denominator here. So this is the transfer function of an all-pass function. The transfer function of the all-pass function divided by 2 is equal to 1 over 2 minus S omega null over Q divided by the conventional denominator. Well, this part here of the transfer function, what kind of transfer function is it? There is just one S at the numerator, so it is a bandpass transfer function. So the transfer function of an all-pass is 1 over 2 minus the transfer function of a bandpass. How can we realize 1 over 2 as transfer function? With a voltage divider. The voltage drop across R1 is equal to the voltage drop across this second R1. This means that at this point we have VI divided by 2. Okay? Then we need the second branch, which is subtracted. And to implement the second branch, we can rely on the circuit that we have already seen. Okay, so the bandpass. Here it is, the bandpass. Okay, so resistance in series with a parallel between capacitance and inductance. Resistance, capacitance, and inductance. And we pick up the voltage at this point. So the voltage drop between this node and this one is coincident with the output of an all-pass function. Okay, so we can realize the all-pass circuit in this way. Okay. So this is based on discrete components. So this implementation of second-order transfer function. So we have resistors, capacitances, and inductances. Can we use this scheme for integrated circuit? Well, the answer is no, because in integrated circuit that is on chip, on silicon chip, you can build resistances, you can build capacitances, but inductances are very, very difficult to be implemented on silicon. Okay, so for capacitances, in fact, you have quite important non-idealities, because you can just realize capacitances by, let's say, creating parallel plates with the vertical or horizontal orientation by exploiting the metallizations in your circuit. But to realizing inductors on chip, it is very difficult. You cannot really realize coils on a planar surface. Okay, what you can do is to implement spirals. Okay, but at the end of the day, when you instance a device like this, you don't really get a simple inductance, but typically you get a much more complex circuit, including a lot of parasitic effects. Okay, so there is a huge problem in realizing inductors on chip. So the paradox is that you can achieve just small inductances values with this on-chip realization, which are related to so-called low Q, low quality applications. Okay, these very small inductances may be used to implement very high frequency filters, but they are not suitable for, let's say, audio applications or application at relatively small, low band. Okay, so how can we cope with this problem? Well, we can do it by exploiting the so-called Antonio circuit. So the Antonio circuit is shown in this slide, and basically the idea is to emulate the behavior of the inductance with this combination of passive and active components, including the op-amps. You see the result. So if you look at the impedance between this point and this one, and you measure therefore the relationship between the applied voltage and the current, what you will find is that the impedance is provided by this expression, which is S time the circuit parameters, C4, R1, R3, R5 divided by R2. Okay, so the bottom line is that you have S, which multiplies something else, okay, which is the typical expression that you have for impedances associated to inductive behaviors. Okay, so your L in this case is given by this factor. Okay. So you are substituting or simulating the inductive behavior of an inductance L with this combination. Okay. And you can set the value of the inductance by controlling these parameters. Okay. You, as designer, will set the value of R1, R3, R5, R2, and C4. Okay, so by setting this parameter, you can control the value of the inductance of the simulated inductance. Let's see how this inductor replacement works in practice. So the reason why the impedance is indeed this expression here. Well, it might be scaring, okay, going through the analysis of all the circuit, but indeed it's not that much complicated, because we are assuming that the op-amp behavior is ideal. Therefore, we are assuming that no current flows as input to the terminals of the input terminals of the op-amp, and that the gain is sufficiently high so that we can assume that we have a virtual short circuit between this node. And the same applies also to the second op-amp. So the idea is that if we are applying V1 to this node, this means that V1 is duplicated here, here, and here. Okay, so V1 is the same voltage which is applied to this resistor. Okay, because of the virtual short circuit induced by the op-amps. So when you have the information concerning the voltage applied to the resistor, you can compute the current, okay, by virtue of the Ohm law. And this very current, this current here is the same current which flows through C4, because there is no alternative path. Okay, no current can flow here. So V1 over R5 is the same current which flows here. Okay. If you know the current which flows in an impedance, such as the one realized by C4, you can compute the voltage drop across the impedance by reapplying the Ohm law. So you can compute the voltage potential that you have at this node, which will be V1 plus the voltage drop across the impedance associated to this capacitance. Okay. So you have the voltage here, you have also the voltage here, because again is V1, so you can compute the current which is flowing through the resistor R3. The current is given by this expression, and this current is the same current which flows in R2, because no current can flow in this path, no current can flow in this path, so there is no alternative path for this current but the one consisting in R2. So you can compute the voltage drop over R2, and then you estimate the voltage drop over R1, and finally you compute the current which is flowing in R1. And once you compute this current, you have the value of I1, because I1 is the same current which flows in R1. Okay, so after all these passages, which are quite basic indeed, so it's an alternative computation of currents and voltages just by applying the Ohm law. Okay, so it's quite cumbersome, the whole procedure, but also straightforward. Okay, so if you go through all this calculation, the final result is precisely what I have anticipated. So all this circuit is equivalent to an inductance. So what we can do is to cut off the inductance from the schemes and the topologies that we have seen so far and replace the inductance with all these components. Okay, so this is what is shown for the case of the generic resonator. So you remove this inductance here and you plug the circuit proposed by Antonio. Okay. And you get the same effect. Okay. One fundamental issue when you are realizing circuit based on the LCR inductor is then you cannot plug the load directly connected to the output node. Because if you do so, you are changing the characteristic of the resonator. Okay, so you need a sort of decoupling to avoid any troubles. Okay, so you add a buffer and then you have the load. Okay, in this way, the buffer is typically characterized by a very high input impedance. Ideally, this input impedance is infinite, so it has no effect on the inner node of the LCR resonator. Okay, so that's the reason why you see this this buffer here. So you are not plugging V out directly to the this node, but you are inserting a buffer in between. The buffer, by the way, can be realized with the conventional non-inverting configuration. Okay, so you can use a non-inverting configuration to pick up the value at this node and send it to a load. These are some other examples. So the low-pass filter that I was sketching in the previous slide is shown here. So R and C are unaffected by the substitution of the inductance. So here we have R6 and C6 replacing these values. And then you replace L with the Antonio circuit. All this part is the substitution of the inductance. Here we have the output voltage, this part, but we need the buffer to decouple the load with respect to the node of the LCR resonator. Similarly, we can sketch the high-pass version from the substitution of the inductance L here with the Antonio circuit. Okay, and then you will find in the next slide all the different combinations. Okay, nothing. The game is the usual. Okay, so extract L, replace it with the Antonio circuit for all combinations. So basically all the topologies that we have seen so far, bandpass, notch, etc., can be replaced with this toxic. Okay, I'm not going through all the combinations because it's a pure mechanical work. Okay, just unplug and replug the Antonio circuit. Okay, in this table you can find the precise relationship between all the capacitances and resistors and the actual transfer function that you are implementing. Of course, since you are specifying the inductance value with 5 parameters, 5 circuit parameters, you have a lot of degrees of freedom to select the values of the different resistors and the capacitors to replace the inductance. Okay, so you can take advantage of these degrees of freedom because to pick up the value of the capacitors and resistors, maybe the ones that you have already stored in your comp. Okay. Okay, let's make a short break and then we will go through some other details. Okay, guys. So indeed, in this table in the study material, you can find all the details related to the transfer function that you can achieve with the implementation that you have seen in the previous slides. An important concern is related when substituting the inductance with the Antonio circuit to the limit of the assumption that we made for the op-amp itself, that is infinite input impedance and virtual short circuit. So this is true just in a limited range, in a limited frequency range, because when the op-amp it is typically characterized by the presence of one pole. Well, this extra pole is added to the whole feedback loop. Okay, so what happens in practice is that the true inductive behavior, so the linear relationship between the impedance and frequency in an Antonio circuit, is valid just up to limited frequencies. So, for example, if the cutoff frequency of the op-amp is around 0.5 megahertz, then you see that the inductive behavior of the Antonio circuit is valid just up to this relatively low frequency, 70 kilohertz. Okay, after this frequency, in which we have a sort of resonance, okay, we have paradoxically a capacitive behavior. Okay, so the impedance decreases with increasing frequencies. So if the cutoff frequency of the op-amp is slightly larger, 5 megahertz, then let's say the corner frequency between the inductive and the capacitive behavior is around 56 kilohertz, and so on. So you need a 50 megahertz cutoff frequency to get a sufficiently, well, a quite high corner frequency between the inductive and capacitive behavior. So you must always take into account the limitations that you have in the actual behavior of your circuit. So you are not using ideal circuits, you are implementing real circuits. A possible alternative to the LCR machinery is the usage of so-called B-quad circuits. Okay, the idea related to this B-quad circuits is that basically you have a different mean to implement a second-order transfer function, which is based on the analysis of what the high-pass frequency transfer function, how this transfer function is related to the input itself. Okay, so just 1 second. So the idea of the big biquad circuits is then to apply two integrators in a feedback loop, okay? Actually, in multiple feedback loops. The first integrator is characterized by this transfer function. Okay, it is an inverting integrator, like the one that we have seen in the previous chapter. Then we have out of the integrator a second. Well, this is the output. So the high pass filter is passed through this integrator, and we get this this term. And finally, we pass this through another integrator to get this term here. So we must relate this behavior to the transfer function associated to the high-pass filter. So basically, the high-pass filter, the relationship between the high-pass filter output, and the input is given by this expression. We have a certain constant which multiplies S to 2 because the high-pass filter is characterized by two poles in the origin, two zeros in the origin, sorry, and then we have the conventional denominator. So S to 2 plus S, which multiplies omega null over Q, plus omega null to 2. Okay, we can now rearrange this formula by taking into account, so let me jump back to the whiteboard. So again, VHP over VI is equal to K times S to 2 over S to 2 plus S omega null over Q plus omega null to 2. If we move this denominator in the left-hand term and VI in the right-hand term, we get this formula. VHP, which multiplies S22 plus S omega null over Q plus omega null to 2 is equal to K S22 times VI. Then we can divide times S to 2 the left and right hand term. And we get this new expression. VHP plus omega 0 over Q times S times VHP plus omega 0 to 2 times VHP over S to 2, which is equal to K times VI. So if we move this term to the right-hand term of the equation, we have that VHP is equal to K times VI minus 1 over Q, which multiplies omega null over S times VHP, plus, minus omega null to 2 over S to 2 times VHP. So you see that the high-pass effect can be seen as the result of the combination of the input signal with 1 over Q time the effect of the integrator, applied to VHP itself, and the double integrator applied to VHP. So then please remember that the integrator can be realized with this circuit. Okay, and this is precisely an inverting integrator. So you plug VI in another circuit in which the other terms are -1/q times the integral of VHP according to the time constant 1/omega0. And a second additional term is omega0 to 2 over S to 2 VHP, and you get as output VHP. Okay, so basically here you are to implement a feedback loop in which VHP it is passed through an integrator, and the second feedback loop in which VHP is passed through a double integrator. So the idea is that the circuit can be modified in the following way. So again, VI is fed through this adder. Well, actually can be multiplied by this factor K. Then here you need two additional feedbacks to get VHP. The first feedback is achieved by integrating VHP according to the time constant omega0, 1/omega0, and you bring this result back to the adder with a multiplication factor which is 1/q. And then you have this term here, which passes through a second integrator. And this second integrator is also attached to a feedback loop, which represents this term here. So we need an additional multiplication time -1, because minus and minus is plus omega0 over S to 2. And then we need to subtract this term in this mixing circuit. Okay, so mixing circuit, integrator 1, integrator 2, and we get VHP. Okay. Well, it is interesting to analyze what is the result of this first integrator. So the output at this point, let's call the output here V1. And then the output at this point, let's call this output V2. Which kind of transfer function do they implement? Well, V1 is VHP multiplied by -omega0 over S, while V2 is VHP multiplied by omega0 to 2 over S to 2. But VHP is given by this expression here. Okay, so we can plug this expression and replace it in the previous one. So this is VHP. Then let's multiply this term times minus omega null over S. So what we get is S22 plus S omega null over Q plus omega null to 2. That's the denominator, as usual. And the numerator is K times omega null with the sign minus, and S22 divided by S, so S. Okay? So what is interesting is that the output V1 is the output of a bandpass filter. Okay, because we have just 1 0 at the origin. If we repeat the same analysis for V2, we have K S22 over S22 plus S omega null over Q plus omega null to 2 time omega null to 2 over S22. If you compute this result, is what you get is K time omega null to 2 over S22 plus S omega null over Q plus omega null to 2. What kind of transfer function is this? Low pass. So what is interesting is that if we find a way to implement a circuit like this one with all this feedback loop, we have the possibility with one single topology to implement in one shot an high pass filter, a band pass filter, and a low pass filter. So this is indeed the idea, once again duplicated in this plot. So the idea is the high pass filter can be realized with these feedback loops. And this is the circuit that we have discussed in the previous whiteboard analysis. Okay, so how can we implement this topology in practice? Well, we need a circuit which is capable to realize this summation, and then we need two integrator circuits. This is precisely what is called the KHN biquad combination. So you see that the mixing circuit is realized by using this op-amp with multiple inputs in the negative input terminal and in the positive one, because we need either to combine positively the output of the integrator or to subtract the output of this second integrator. And then we have this circuit here, which is replacing the integrator expression. Okay, we already know that this functionality here can be realized with this guy. Okay, so this is the integrator, which is replaced by this guy. We need a second integrator. Here it is. Okay, the output of this integrator is fed back to the mixing circuit, and similarly, the output of this integrator is moved back to this mixing open. Okay, so let's try to investigate the behavior of this KHN and find the transfer function, the global transfer function. So the KHN is indeed a circuit like this. So we have the first mixing op-amp, which combines multiple inputs. The input related to VI on the positive input terminal. Then in the negative input terminal, we have a feedback loop, which is needed to perform all the summing and subtracting tasks. Then we have a macro loop in which we have the resistance R1. Then we have a series of two integrators, which are realized with conventional inverting configuration. The time constant RC set the value 1 over omega null. The same time constant is used in the second integrator. The second integrator output is provided to the macro feedback loop, while the first integrator output is given here in this conditional feedback loop, which is indeed a quite critical one, because the feedback it's the positive input of the op-amp. Okay, this could be a problem, but the integrator here is inverting, so this problem it is somehow mitigated. So this resistance is R3. This resistance is R, like this one. This is C. This is C. This is R sub F feedback, and this is R2. Now, what we want to do is to determine the relationship that we have here. Okay, so to find the actual value of VHP, taking into account the circuit parameters. We will analyze this circuit by applying the superposition principle. That is, we will compute the coefficient of proportionality K1 between VHP and VI, the input, when the bandpass value, that is this voltage here, and the low pass value, that is the voltage here, are equal to 0. Then we will compute the second coefficient, K2, which relates VHP to V bandpass when VI and VLP are equal to 0. And finally, last term, to apply the superposition principle, is the computation of the relationship between VHP and VLP when the other quantities are equal to 0. So combining these three terms, we get the transfer function. Proceeding this way is much more convenient than analyzing in one shot the whole circuit. Okay, because indeed, when we are analyzing K1, we are assuming that the VBP and VLP are equal to 0. This means that in this condition, this node is grounded, and also this node is grounded. Okay? So we can simplify a lot of the analysis because we have no feedback loop through the first integrator and no feedback loop through the second integrator. So basically, let's call it the red circuit is just VI facing R2. R2 is connected to R3, which is grounded. Then this is the input of the op-amp, the positive input. Then we have the feedback loop through RF. And R1, which is connected to RF, is also grounded in the second terminal. So can you help me in finding the relationship VHP over VI for this circuit? So first of all, you can compute the value V+. So V+ is achieved from VI by taking into account the effect of the voltage divider. So can I zoom out? You see the circuit if I'm zooming out? Can you read the characters? Yeah, okay. So for a circuit like this, V+ is R3 over R2 plus R1 time VI. Okay, V+ is the input of a non-inverting configuration. Therefore, V out, so VHP in this case, is equal to V+ time 1 plus RF over R1. The bottom line is that K1 is the multiplication of this factor times this one. So 1 plus RF over R1 times R3 over R2 plus R1. Now let's focus on K2. The circuit related to K2 is a circuit in which VI is grounded and also the low pass terminal is grounded. And the unique input is provided by the bandpass. So yeah. Thank you. R3. And the same mistake is here, sorry. A conventional voltage divider expression. What is the appearance of the green circuit? Okay, the green circuit is something like this. We have VBP, which is the input attached to resistor R3. Then R3 is facing R2, which is then connected to the ground. Altogether, these two devices are connected to the positive input of the op-amp. And then we have the feedback loop through RF and the loop connected to the ground through R1. Okay, and this is VHP under these conditions. So in this particular case, K2 is given by the effect of this voltage divider. The unique difference is that in the previous case, we had R2 and R3, and now we have R3 and R2. So we have just to flip the expression that we have computed before, R2 divided by R3 plus R2. And then we have the effect of the non-inverting configuration, so 1 plus RF over R1. Okay? Do you want me to turn on the light? Better? Okay. So this is the green circuit. Let's compute the last one, the orange, which is related to the combination in which the low-pass filter is the unique active terminal, while VI and V bandpass are equal to 0. So let me move these guys away. So that I have some free space to sketch the orange circuit. So in the orange circuit case, both VI and V bandpass are grounded. So the new circuit is something like this. The positive input is connected to the parallel between R2 ground and R3 and ground. And then we have a feedback loop through RF. And finally, R1 is connected to VLB. So with an input like this, V plus gets equal to 0. And VHP is just given by minus RF over R1 times VLB. So minus RF over R1 is K3. Okay, so I have to combine this first expression with the second one, with the third one, to get the full picture. So VHP is equal to K1, so 1 plus RF over R1 which multiplies R3 over R2 plus R3, which multiplies VI, plus the second term, K2, which is R2 over R3 plus R2, which multiplies 1 plus RF over R1. This term here multiplies VPP, but the voltage related to the bandpass term, it is also given by the integral of VHP, so minus omega null over S times VHP. Okay, because if we look at this circuit, we know that VBP is VHP integrated. The last term is K3. K3 is minus RF over R1, is the last one which we have calculated. And VLP is resulting from the double integration of VHP. Okay, so the KHN circuit produces this transfer function. We can compare the resulting transfer function from the circuit calculations, so from the circuit analysis, with the pure abstraction which we have analyzed at the beginning of this class. So VHP should be K times VI plus 1 over Q times minus omega null over S VHP plus, minus omega null to 2 over S to 2 times VHP. Okay? So please remember that VHP over VI is given by this expression, K times S to 2, S to 2 plus omega null over Q times S plus, plus omega null to 2. And please also remember that this is related to the pole positioning with respect to the imaginary axis. So omega null is related to this distance, the distance between the pole and the origin, and the factor Q is related, is higher the closer are the poles to the imaginary axis. So the idea is that from our specification, we will get the value of omega null and Q, which are necessary to implement the specific filtering effect. And then we have to translate this omega null and Q into circuit parameters to achieve the proper implementation. Okay, so the design steps are this one. Okay, starting from the specification, you find omega null and Q, and finally you find the topology and the circuit parameters which implement that particular value. So in this specific case, we need that the formula, the top formula, is equivalent to be equivalent to the pure abstraction. Okay. Okay. We have the numerical value of omega null and Q, and we want that the resistors are perfectly tuned to set that specific values. So how can we achieve this in practice? So first of all, we have to compare the last term. So the last term in the circuit implementation is minus RF R1 omega null to 2 over S to 2 VHP, while in the pure abstraction is omega null to 2 over S to 2 times VHP. This means that the first important step is to set RF equal to R1, so that this coefficient becomes equal to 1, which is what we want. Okay? Then we want that this term here is equal to this 1 over Q. Okay? But we have also said that RF is equal to R1, so this is 1 plus 1. Okay? So second step, let me cancel this. Second step, twice R2 over R3 plus R2 must be equal to 1 over Q. Okay, so this 2 is related to this term here. So 1 plus RF over R1 is 2, because RF is equal to R1. Okay, so twice R2 over R3 plus R2 must be equal to 1 over Q. With some algebraic manipulation, you can show that this means that R3 over R2 must be equal to 2 times the quality factor minus 1. Again, please remember that the quality factor is something that you derive from the specification. Okay? So once you know the factor Q, you know what should be the ratio between R3 and R2. Finally, you have to implement the last equality. That is, you want this term to be equal to this one, okay? Because the coefficient of VI must be equal to factor K. So third condition, this is 1 plus RF over R1, so this is 2. Multiplying R3 over R2 plus R3 must be equal to K. Okay, if you plug this relationship in here, basically you can divide numerator and denominator time R2, and then you get 2 times R3 over R2 divided by 1 plus R3 over R2, and then you can substitute this term. What you get by applying this calculation is that the factor K shall be equal to 2 minus 1 over quality factor. Okay, so this means that basically the high frequency gain of the high pass filter is somehow set by the quality factor in the KHN implementation. Okay. So we have completed the analysis of the KHN factor. So a KHN, sorry, biquad. What is interesting is that by properly combining all these terms, you get in one combination, the low pass, band pass, and high pass filtering effects. So you can use the same configuration to achieve this goal. Of course, each configuration is characterized by the same omega null and same Q. Okay, so you cannot realize at the same time a low pass filter and a high pass filter with different omega null values. Okay, but you have this opportunity. Next time we will analyze other configurations. For example, the so-called Tau-Thomas bicode, and finally we will find a way to achieve a second-order transfer function with just one OPA. Okay, it's a so-called Salmon and Key implementation. Okay, thank you very much for your attention. I guess that next time will be not this Friday, but on Monday, because if I remember well, there is the stop of the classes due to final exams. Well, we will check. Okay. Arrivederci. Bye bye.